Okay, this is going to be my lab report for Lab 4 of Physics 2211, and this is going to be over oscillating motion. For this lab, there are several key principles we need to understand. First of all, there's Newton's second law, which is force times mass, or force equals mass times acceleration. Using this, we can determine the mass of the system. We can also use this to determine several other important um, equations for this formula, for this lab, sorry. And we're also going to need to know the energy principle, which we know is that the energy is neither created nor destroyed in the system, meaning that throughout the entire system, energy is constant. We're going to define the system to be mass, the spring, and the earth. And the surroundings of this system is there's going to be nothing. And by knowing this, we can determine that nothing is influencing the system, meaning that we are not losing energy to anything. The purpose of this lab is to use Tracker to find the motion of an object and then using the forces acting on the object to predict where the object is going to be, also using the oscillation period of the object. There are several key equations we're going to need. So first off, we need to know how to find kinetic energy, which you can see right there, gravitational potential energy, the spring potential energy, and the total energy, which comes out to just be all of those energies added together. There's also going to be several other equations which we needed to know Newton's second law to be able to apply here. First of all, we need to know the velocity update formula, which is V final is equal to acceleration over acceleration times time plus V initial. The position update formula, which is uh, position final is equal to V average times time plus R initial. And to find the period of the oscillation, we are going to need 2 pi square root m over k. For this experiment, as you can see, we use Tracker, as usual with these labs, to track the motion of this object. Initially, time is going to be equal to 0. The starting position is going to be negative 0.33, and then negative 1.85 feet. V initial, as it is leaving the hand of the person letting go of the spring, is going to be equal to 0 meters per second. And we can also know that acceleration due to gravity is going to be 9.8 meters per second squared here. Now, using Newton's second law and the associated equations, we can find that the mass of this object is going to be 0.4 kilograms, the spring coefficient is going to be 6.83, and the length of the spring when it is at rest is going to be at 0.125 meters. Here you can see the computer model that was used to find the graphs that you're going to see coming up. By looking at these models, we can see where we find each individual energy. We can see where we find kinetic energy, gravitational energy, spring energy, and then you can see also that energy total is just found by adding all those together, like we said earlier. Here you can see as the spring moves, and you can see the kinetic energy, gravitational energy, spring energy, all of it coming together, you can see that no matter what happens, the spring or the total spring energy is equal to 0. The gravitational energy and spring energy cancel each other out, and what they don't cancel out of each other is accounted for by the energy of motion, which is kinetic energy. And as you can see on the right, you can see the oscillation of the position as this goes on. Now, what does this mean? In this lab, is the energy principle satisfied? Yes, because no energy is lost in the system that we can account for. It is possible that energy is lost to outside factors such as air resistance, which would create friction, which would cause loss of energy via thermal energy, but that is so negligible here that we can just ignore it. Now, if we found the period of oscillation using the y values, the period would come out to be shorter, which would yield a different result when finding the energy of the system. So that's just something important to keep in mind when finding energy within an oscillating system. And that's going to be all. Thank you.